Hi, I'm Sven, and I like triangles.
That was probably a really bad Sven impression. But you know, if you've ever watched Frozen, I think Kristoff does an excellent Sven impression. I think that's one of the things from that movie that people forget about. Anyway, what a global phenomenon that movie has turned into. But we're going to talk a little bit more about triangles and not Sven necessarily. So we're going to finish up this lesson on angle relationships and triangles by talking a little bit more about angle relationships, but also talking about this second learning target, which really connects to all the success criteria. The one thing that's a little bit different is we're talking about similar figures, and we're going to talk about their sides a little bit too. I know this is a lesson on angles, but they've got in this third part a little bit more about sides as well. So just as a refresher, similar shapes, they have the same shape but different size. So it's a bigger or smaller version. So we talked a lot about similar shapes when we talked about dilations in a previous unit. And so we're going to kind of review some of that, but also tie that into what's true about their angles, which if they're similar shapes, they have the same angle measures, but what's true about their sides as well. Okay? So let's start with number 13 here, and we are in your notes book on page 202. Page 202. All right. We're going to go through this problem as a class here. It says complete the logic to show, you guys know what logic is? Logic is this kind of connects. You could take some patterns, you could take some things you know, and draw conclusions based off of those things. So that's what we're going to do. So complete the logic to show that the sum of the angles y and z equals the measure of w, which is something we've talked about. Remember, exterior angles, that's an exterior angle. Abbreviate here, exterior angle, is equal to the two interior angles that are non-adjacent, so they're not next to it. Those should add up to equal w. So complete the two equations to show the angle relationships you know. X plus y plus z. What do we know about x plus y plus z? Those are the ones on the inside. Those are all equal to 180 degrees, right? Angles inside of a triangle add up to 180 degrees. What about w plus x? W plus x are these two right here next to each other, and they actually form a line, and if a line is 180 degrees, those two added up should equal 180 degrees. Now, it says solve the first equation for the sum of y and z. And solve the second equation for w. So if we were to take that first equation and we want to get the y plus z by itself, we could subtract x here. I know that looks a little silly, but we're going to subtract it. It'll get rid of it. And then we just subtract x over here. So all it would be is y plus z equals 180 minus x, which is kind of interesting if you think about it. We'll see where that leads us. Same thing with the second one. We can solve for w just by getting rid of this x. We can minus x from both sides. Just like if it was a number, we can subtract it from both sides. So that goes away. W is equal to 180 minus x. Now, the interesting thing there is that both of them are equal to 180 minus x. So if they're both equal to 180 minus x, here in the third part it says, how do you know that the angles, the measure of w equals the sum of the other two? Well, if they're equal to the same thing, then they're equal to each other. It's like if two bank accounts both have $100 in them, then they're equal to each other. They have the same amount. So that's what we're saying for this. I know we kind of talked about this yesterday in yesterday's lesson as well, but we can say they're equal to the same thing. Make it a little bit smaller, fit it on here. So they are equal to each other as well. Meaning if they both each equal 180 minus x, then we can say that the y plus z, which is equal to 180 minus x, is equal to the w, which is also equal to 180 minus x. And that shows that our exterior angle is equal to the two non-adjacent interior angles. All right, we just proved something. Let's go down to the bottom. We got two examples very similar. Numbers 14 and 15. We're still talking a little bit about angles, but we're going to start talking about sides as well. So let's look at number 14. In the diagram, angle ABC is congruent to angle DEC. So ABC, that would be this angle, is congruent to this one. Okay, explain how you know that ABC is equal to DEC, or they're similar triangles. So if we said if they have all the same angle measures, then they're similar. We only know that one angle measure is the same right now. But if we look at one of the angles, like angle C is in both of them. So it's equal to itself, obviously. So we have two angles that would be congruent to the two triangles. Now the question is this angle congruent to this angle? And actually, yes, they are. If you go back to what we talked about back on the first day of this lesson, we learned that, I'll pull up here, we learned that if two angles are congruent to two angles in another triangle, then the third angle would be congruent as well. So what we had in this example was that if, sorry, scroll down. If two of the angles are congruent to two angles in this other triangle, then these third angles would be congruent as well. So we could say, if I'm going to put this into an explanation, I'm going to say angle, make it fit, angle ABC is in both triangles. So that's one pair of congruent angles. The other pair of congruent angles was given. And those would be angles ABC and DEC. That was said right away. And since two pairs of angles are congruent, then the third pair is also congruent, making the triangle similar. So really, we just need to know that two angles are congruent, and that would show that the triangles are similar. Now, if we don't have enough with angles, then we're going to need something else with sides as well. So this is where we kind of talked about it at the end of the last day. In similar triangles, the sides are proportional to each other, meaning if let's just say you have one side goes along is 1 and the other triangle goes along with 2, and then you have another side that's 3, that should go along with 6 because it's twice as big. It should be twice, all the sides should be twice as big then, because the whole shape would be twice as big then. That's just an example. But it says in number 15, this diagram shows the same similar triangles that we had above. Each statement or segment except AB is a road. So I'm picturing it as a map now. So AB is the only one that's not a road, that's in water. So between points A and B is a pond. Explain how you can find the distance from A to B by measuring the other distances. So kind of what I was saying there is, if you know that, like let's just say we know AC. Well, I should use this. So we're going to take side AC. If I put that over the corresponding part in the smaller triangle, that would be DC, because they're both that top side. That should be the same ratio. So let's just say it was 1 to 2. That should be the same ratio as BE over the side. So that's the bigger triangle, and the smaller triangle would be EC. So BC and EC. Bear with me here. So if we wanted to find AB, we can use the same ratio it should be equal to, in the bigger triangle, it would be AB. The smaller triangle, the one that goes along with it, the corresponding part, would be DE. So they're proportional. You can use the ratio of, I'm going to put it in the words. All right, there I typed it out. You can use the ratio of one side to its corresponding side in the other triangle. And what I mean by that is, let's just say we knew that AC was, let's just say BC. BC was 2, and EC was 3. And I knew that AB was 4. I could figure out, well, let's just, I shouldn't have 4. AB is what we're trying to find. Let's just say I knew that, what's the one that goes with AB? Oh, AB is the bigger one. Messed that up. Let's erase this. Let's just say we knew BC was 3 and EC was 2. And if we don't know what AB is, we could say that's our X. Can't write an X now either. And let's just say this was 4. DE was 4. Based on that, you can solve your proportion by cross-multiplying, or you can know that multiply by 2, multiply by 2, X is going to end up being equal to 6. That was just an example. I don't have exact numbers here, but that's just an example. You can use that ratio. So let's look at this on page 203 here. We are going to just briefly connect this to one other thing that we've actually learned a little bit of in the past. It says, use similar triangles to explain why the slope is the same between any two distinct points on a line. And this actually goes back to something we learned when we talked about slope. Remember, slope is rise over run. So slope is rise over run. Rise over run. So that's why there's these triangles on there. And you have this line. You can find the slope of that line between any points. Some of you figure this out easier than others, but you pick any 2 points. You can pick this one. I know there's some on there for you. And this one. And my rise over run is 2 over 3. But let's say we picked this one and this one. Then it's 1, 1. That's not even on a point. And they picked bad numbers. Not even on a, this is like, whatever. We're going up 1, 2, 3, 4, and over 1, 2, 3, 4, 5, 6. So it's 4 over 6. Guess what 4 over 6 reduces to? 2 over 3. So you get the same thing, and they're similar triangles. If you look at them, they're both triangles. It's just one's a bigger version of the other. So part A, it says, use the fact that AB is parallel to DE. So we're looking at the examples on there. If you know that AB is parallel to DE, and BC is parallel to EF, you know that certain angles are going to be congruent because there's a transversal. So we can say that corresponding angles are going to be congruent. Okay? Now, if corresponding angles are congruent, that would include angle A and angle D, or that would be angle BAC. Well, we're going to say angle A. We know that angle C is congruent to angle F. So C here and F here. Oops. And then finally the last angle, the right angle. Angle B is congruent to angle E. And that means that it's a congruent or a similar triangle because all three angles are congruent. So part B, explain how you know that the triangles are similar triangles. So that's exactly what we said. I'm going to type this one out. All corresponding angles are congruent. So the triangles are similar. Okay. And finally, part C, it says the slope of the line between A and C is, it says AB over BC. The slope of the line between D and E is DE over EF. Using similar triangles, explain how you know the slope of the line between the both points. Basically, kind of what we talked about on this last problem in number 15. The sides are going to be proportional as well. Just like the angles are equal, the sides are proportional. So I'm going to leave it at that for right now. Just know that if one corresponding side multiplies by 2 to get to the other one, then that's going to work for all the pairs that correspond. So like, if I were to write that out, it would be saying that AB over BC should be equal to DE over EF. I don't want to get too much into that, so we're going to leave it at that because I wanted to focus more on the angles because that's what this whole lesson is about. But we're going to end this lesson here. Again, connecting what we've been learning about angles to similar triangles here in day 3 of this lesson 22. All right, see you next time.